In 1915, a South African astronomer named Robert Innes pointed his telescope at a faint star in the constellation Centaurus and noticed something extraordinary. That star was moving. Not like all stars, with the slow drift that accumulates effects only over timescales of thousands of years. This one was moving in a measurable and obvious way, different from nearby stars, and when Innes calculated its distance, he understood why that star was behaving so peculiarly. It was the closest to us, the closest of all. He called it Proxima Centauri. Proxima, from the Latin, the next, the neighbour, and it's still there, invisible to the naked eye, part of a triple system we call Alpha Centauri, the most cited destination in the history of science fiction, the place where, in novels and films, we send our first probes, our first astronauts, our first voice into the universe. 4 light years and 200,000, they always say, as if it were a simple thing to say. How many kilometres separate you from the ceiling above you? 3 meters, maybe 4. And how many kilometres separate that ceiling from the moon? About 384,000 kilometres. A distance that seems enormous, and in a way it is. Big enough to contain 30 planet Earths in a row, one after the other. And from the Sun, 150 million kilometres. It takes light a full 8 minutes to travel that distance. This means that the Sun you saw today wasn't the Sun as it is now. It was the Sun as it was 8 minutes ago. You were looking into the past. Keep this feeling in mind. The past presents itself as the present. It will return. Now take all these distances, the moon, the sun, all that immense space you just imagined, and put them aside for a moment. Because compared to what we're about to discuss, these are basic measurements. It's the distance between the kitchen and the living room. A light year is approximately 9 trillion kilometres. Alpha Centauri is 4.2 light years away. Tonight we'll really understand what that means. The speed of light is 300,000 kilometres per second. Not as fast as a bullet, not as fast as a jet, not as fast as anything you've ever seen move with your own eyes. 300,000 kilometres every single second. In the time it takes you to blink, light has already travelled enough distance to circumnavigate the entire Earth 7.5 times. As you read this sentence, light has crossed the continental United States from one end to the other, approximately 1,000 times. This is the fastest thing in the universe. Not approximately the fastest. The fastest. As far as physics is concerned, nothing with mass can reach it. Nothing can exceed it. It's the absolute speed limit of reality, inscribed in the very fabric of space-time. Einstein spent years working out what all this meant, and the conclusions were so strange that many of his colleagues initially refused to accept them. Time slows as you approach the speed of a light. Mass increases. Space contracts in the direction of travel. The universe bends its laws to keep that limit intact. Yet light still takes 4.2 light years to reach Alpha Centauri. Think about that for a moment. The fastest thing in existence, travelling non-stop without deceleration, without stopping to rest, refuel or recalculate, would take 4.2 light years to cover that distance. 4 years. More than 4 years of continuous travel at 300,000 kilometres per second. That's what 4.2 light years really means. Not a number, a duration, a sentence, a commitment of time so long that children are born, learn to walk, and start school in the time it takes light to complete the journey. There is a spacecraft currently leaving our solar system. It is called Voyager 1, and it is the most distant human-made object in the history of civilization. Launched in September 1977, it has been travelling through space for nearly 5 decades without stopping, without slowing, without any intention of returning. It crossed the boundary of the heliosphere, the region where the Sun's influence finally yields to interstellar space, in 2012. As of now, it is roughly 23 billion kilometers from Earth. That sounds like an almost incomprehensible achievement, and in human terms, it absolutely is. Voyager 1 represents one of the most extraordinary engineering accomplishments our species has ever produced. A machine the size of a small car, built in the 1970s, still transmitting data across a distance so vast that its radio signals, travelling at the speed of light, take more than 22 hours to reach us. 22 hours for a signal moving at 300,000 kilometers per second. Engineers at NASA's Jet Propulsion Laboratory have to account for where the spacecraft will be by the time the message arrives before they even send a command. They are not talking to Voyager as it is. They are talking to where it will be. And yet, when you plot Voyager 1's position against the distance to Alpha Centauri, something quietly devastating becomes clear. After nearly 50 years of continuous travel, after crossing the entire span of our solar system and pushing into the interstellar void, Voyager 1 has covered approximately 1/500th of the distance to Proxima Centauri. Not 1/5, not 1/50th, 1/500th. If the journey to Alpha Centauri were a marathon, 42 kilometers of road stretching ahead, Voyager would have completed roughly 80 meters, less than the length of an Olympic swimming pool. At its current speed, Voyager 1 would reach Alpha Centauri in approximately 73,000 years. Let that number breathe for a moment. 73,000 years ago, modern humans had not yet left Africa. There were no cities, no agriculture, no written language, no wheels. There were no nations, no borders, no religions as we understand them. The cave paintings at Lascaux, often cited as one of humanity's earliest expressions of artistic consciousness, wouldn't be created for another 50,000 years. The entire recorded history of human civilization, every empire and revolution and scientific discovery and cultural transformation, fits comfortably inside the last 5,000 years. Voyager's journey to Alpha Centauri would require 14 of those entire spans laid end to end. And Voyager is not slow by the standards of what we have built. It is travelling at approximately 61,000 kilometres per hour. That is fast enough to travel from New York to London in under 4 minutes. Fast enough to circle Earth's equator in roughly 40 minutes. By any terrestrial measure, by any scale derived from human experience, it is moving with almost inconceivable speed. The fastest trains on Earth travel at around 600 kilometers per hour. The fastest aircraft, experimental and military, push past 7,000. Voyager moves at 61,000. It is nearly 9 times faster than the fastest plane ever flown, and it would still need 73,000 years. This is the moment when the distance to Alpha Centauri stops being a number and starts being something else. Something heavier, something that sits in the chest differently than a statistic. Because Voyager isn't a thought experiment. It isn't a hypothetical spacecraft in a physics textbook. It is real. It exists. It was built by human hands, launched by human decisions, and has been travelling through interstellar space for longer than many people reading this have been alive. It is our best effort, our farthest reach, our most distant ambassador to the cosmos. And our best effort, our farthest reach, our most distant ambassador, would take 73,000 years to reach our nearest neighbour. Let us try to make this real in a different way. Numbers, even enormous ONAs, have a way of sliding off the mind. 73,000 years remains abstract. 4.2 light years remains abstract. What the brain needs is not a larger number, but a different kind of picture. So let us build one. Imagine you are holding a standard globe of Earth, the kind that sits on a desk or a classroom shelf, about 30 centimeters in diameter. Now imagine you want to place Alpha Centauri on that same scale. If Earth were this globe, where would the Sun be? At this scale, the Sun would be a sphere roughly 3 meters in diameter, positioned about 320 meters away from you. Not in the next room. Not at the end of the hallway. 320 meters, 3 city blocks. Already the solar system is larger than it felt a moment ago. Now, on this same scale, where would Alpha Centauri be? 87,000 kilometers away. To place Alpha Centauri accurately on a globe-scaled model of the solar system, you would need to travel more than twice the distance from Earth to the Moon. The model would not fit in a room. It would not fit in a city. It would not fit on the continent. You would have to float your Alpha Centauri marker somewhere in deep space, beyond the Moon's orbit, to accurately represent how far away it is relative to Earth H at this scale. This is the first time most people genuinely feel the distance rather than simply knowing it. Because the Moon feels far. You can look at it tonight and feel the gulf between you and that pale disk hanging in the sky. And yet, at globe scale, that entire gulf, that entire emotional and physical distance to the Moon, is less than the space between us and our nearest star. Now let us try another scale. This one used by astronomers when they want to make the solar system feel manageable. Let us shrink everything so that the distance from Earth to the Sun equals 1 meter. A single meter, about the length of a child's arm stretched wide. On this scale, Mars is 1.5 meters away, Jupiter is 5 meters. Neptune, the outermost major planet, sits about 30 meters from where you're standing. A large room captures the entire span of our planetary system. Where is Alpha Centauri? 270 kilometers away. At a scale where our entire solar system fits in a large room, the nearest star is 270 kilometers outside that room. If you place the Sun on the floor of a building in the centre of London, Alpha Centauri would be somewhere near Paris. Not in a neighbouring building. Not down the street. In another country. And these are the closest stars, the nearest neighbours, the absolute minimum distance between star systems in this region of the galaxy. Most stars are much farther. The galaxy itself is 100,000 light-years across. The Andromeda Galaxy, the nearest large galaxy, is 2.5 million light-years away. These distances don't scale up from Alpha Centauri. They explode beyond it in ways that require entirely new frameworks to contemplate. But we are not going to Andromeda tonight. We are only going to Alpha Centauri. And as the scales keep showing us, that alone is enough. That single step, 4.2 light-years, the smallest interstellar distance imaginable, already places us in a realm where everything we've ever built, every vehicle, every rocket, every probe launched with every gram of engineering ingenuity our civilization possesses, becomes almost comically inadequate. The universe is not keeping us out. There are no walls, no barriers, no force actively preventing us from leaving. The distance itself is the barrier, silent, indifferent, and absolute. So let us talk about what it would actually take. Not in the language of science fiction, where ships fold space and crews emerge blinking from suspended animation to find alien suns hanging in the viewports, in the language of physics, in the language of what the laws of nature actually permit, what engineering might plausibly achieve, and what the numbers say when you push them as hard as they will go. The first honest question is this: how fast could we actually travel? Chemical rockets, the kind that have carried every human being who has ever left Earth, work by burning fuel and expelling the exhaust at high velocity in the opposite direction of travel. This is straightforward Newtonian physics, action and reaction. The problem is that chemical rockets are extraordinarily inefficient in terms of the ratio between the energy they release and the speed they can achieve. The Saturn V, the most powerful rocket ever successfully launched, sent Apollo astronauts to the Moon at speeds of around 40,000 kilometers per hour. Impressive by any earthly standard. But at 40,000 kilometers per hour, a journey to Alpha Centauri would take approximately 115,000 years. Engineers know this. They have known it for decades, so they have imagined other systems. Ion drives use electric fields to accelerate charged particles and expel them as thrust. They are extraordinarily fuel efficient and can operate continuously for months or years, gradually building up speed in a way chemical rockets cannot. The Dawn spacecraft, which used ion propulsion to visit two separate bodies in the asteroid belt, demonstrated the technology beautifully. The problem is thrust. Ion drives produce tiny amounts of it, measured in millinewtons, roughly equivalent to the weight of a piece of paper resting on your hand. Given enough time and enough fuel, they can accelerate a spacecraft to impressive speeds. But impressive here remains a relative term. Current ion drive technology, scaled optimistically, might push an unmanned probe to perhaps 150,000 kilometers per hour. At that speed, the journey to Alpha Centauri takes a little over 30,000 years. Better, still geological. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, typically hydrogen, to extreme temperatures and expel it as thrust. This can achieve exhaust velocities roughly twice those of chemical rockets, which translates to significantly higher final speeds. Various designs were tested in the 1960s and early 1970s under programs like NERVA in the United States. They worked. They were never flown in space, partly for political reasons, partly because the destinations anyone was interested in at the time didn't require them. With nuclear thermal propulsion and a long enough acceleration phase, a spacecraft might reach several 100,000 kilometers per hour. This brings the Alpha Centauri transit time down to somewhere in the range of 10 to 15,000 years. Still longer than recorded human history, nuclear pulse propulsion is more extreme. The concept, studied seriously under Project Orion in the late 1950s, involves detonating a series of small nuclear explosives behind a spacecraft equipped with a massive pusher plate. Each detonation accelerates the ship. Thousands of detonations over time could theoretically push a large spacecraft to speeds approaching 1/10 of the speed of light. At that velocity, the journey to Alpha Centauri would take roughly 42 years, a human lifetime, a long career, the kind of duration a person could, in principle, survive. 42 years of travel at 1/10, the speed of light, inside a vessel kept alive by controlled nuclear explosions occurring every few seconds, carrying enough fuel to sustain thousands of detonations, shielded against the interstellar medium, which at those speeds becomes a lethal radiation environment, maintained by systems that cannot fail because there is no rescue, no resupply, and no way home if something goes wrong. The physics permits it. Barely. The engineering challenges are, by any honest assessment, far beyond anything our civilization has attempted. But the number is no longer geological. It is human-scaled. Uncomfortably, tantalizingly human-scaled. There is a project that took this seriously. In 2016, a group of scientists, engineers, and visionaries announced an initiative called Breakthrough Starshot. The concept was simple to state and staggering to contemplate. Instead of sending a large spacecraft slowly, send an extremely small one fast, not a vessel carrying humans, not even a vessel carrying sophisticated instruments in the traditional sense. A gram-scale wafer, a chip the size of a postage stamp, carrying cameras, sensors, and a communication laser attached to a sail. A light sail. The idea behind light sails is not new. Light carries momentum. When photons strike a reflective surface, they exert a tiny pressure. In the vacuum of space, where there is no friction and no drag, even a tiny sustained pressure can accelerate a sufficiently light object to remarkable speeds. In 2010, the Japanese space agency JAXA successfully deployed Icaros, the first spacecraft to demonstrate solar sailing in interplanetary space. It worked. The physics is real. Breakthrough Starshot proposed to take this to a completely different scale. Instead of relying on sunlight, which weakens with distance, the plan called for a ground-based laser array of extraordinary power. A collection of lasers producing a combined beam of 100 gigawatts, focused on a sail perhaps a few meters across but only a few hundred atoms thick, attached to a gram-scale spacecraft. The laser fires for a few minutes. The sail catches the beam. The spacecraft accelerates to 20% of the speed of light, not 10%, 20%. At 20% of the speed of light, the trip to Alpha Centauri takes roughly 20 years, not a geological timescale, not longer than recorded history, 20 years, within a human lifetime, within the career span of the scientist designing the mission, short enough that the people who build it might live to receive the first data back. The data would take 4.2 years to return, of course, light speed again. You would send a probe, wait 20 years for it to arrive, then wait another 4 years for its signals to reach you. But the signals would come, and what they contained might be the most important information our species has ever received. The challenges are immense and deserve honest accounting. A 100 gigawatt laser array does not exist. The most powerful continuous laser systems currently operational measure in the kilowatt to megawatt range. 100 gigawatts is roughly 10 times the total electricity generating capacity of the United Kingdom. Focusing that beam with sufficient precision across the distance needed to fully accelerate the sail requires optical systems of a quality that doesn't currently exist. Keeping the sail stable and aligned within the beam during acceleration, a process that takes only a few minutes but involves forces acting on a structure thinner than a soap bubble, is an unsolved engineering problem. Then there is the question of interstellar travel itself. At 20% of the speed of light, individual hydrogen atoms floating in the interstellar medium hit the spacecraft with the energy of cosmic ray particles. Over the course of a 20-year journey, the cumulative effect could be significant. Shielding a gram-scale chip against this bombardment without adding prohibitive mass is a materials science challenge at the edge of current understanding. And communication. A laser powerful enough to send signals across 4.2 light-years from a chip-scale transmitter, powered by whatever energy the sail can harvest, pointing precisely at a moving target, Earth, across that distance, is another problem with no obvious solution today. But here is what matters. None of these are violations of physical law. Every single one of them is an engineering problem. A hard engineering problem, perhaps the hardest suite of engineering problems ever assembled in a single mission concept, but problems of the kind that human ingenuity has a history of eventually solving. When the challenges of the Saturn V were first laid out in the early 1960s, the gap between what existed and what was needed was enormous. 12 years later, human footprints were on the moon. 20% of the speed of light. 20 years. A postage stamp riding a beam of light toward the nearest star. It sounds like poetry. It might also be the most honest plan we have ever made. But let us stay with the human body for a moment, because everything discussed so far has been about machines, about propulsion systems and laser arrays and gram-scale wafers riding beams of coherent light across the interstellar void. And machines, for all their limitations, do not get lonely. They do not get hungry. They do not lie awake in the dark wondering if anyone remembers them. They do not need air or water or the particular quality of afternoon light that makes a person feel, without being able to explain why, that everything is going to be all right. if we are ever going to send human beings to Alpha Centauri, we need to think about what that actually means for the organism doing the travelling. Start with the most basic constraint. The human body was not designed for space. This is not a poetic observation. It is a precise biological fact. Every system in your body, your cardiovascular system, your skeletal structure, your immune response, your neurological architecture, was shaped by billions of years of evolution on a planet with a specific gravitational field, a specific atmospheric composition, a specific cycle of light and darkness, and a specific microbiome that your body learned to coexist with over the course of your entire life. Remove any of these things, and the body begins to respond in ways that range from inconvenient to life-threatening. In microgravity, the human heart gradually changes shape. Without the constant effort of pumping blood upward against gravity, it becomes rounder, more spherical, less efficient. Fluid shifts toward the head, creating chronic pressure that can damage vision permanently. Astronauts returning from long missions on the International Space Station sometimes cannot walk unassisted for days. Their bones have lost density, their muscles have atrophied, their sense of balance, recalibrated to an environment without a clear up or down, struggles to reorient to a world that insists on having both. The longest continuous human spaceflight on record is just over a year. Russian cosmonaut Valery Polyakov spent 437 days aboard the Mir space station in the mid-1990s, specifically to study the effects of long-duration spaceflight on the human body. What he and subsequent studies revealed was not encouraging for interstellar ambitions. After a year in space, the physiological damage is measurable, significant, and in some cases only partially reversible. The immune system dysregulates. The gut microbiome shifts in ways that are not fully understood. Cognitive performance changes in subtle ways that astronauts themselves often don't notice until they return. Now scale this to a journey of 20 years, or 40, or if we're using anything close to current propulsion concepts, thousands. Even at breakthrough starshot speeds, a crude version of that mission, if one were ever conceivable, would take 20 years. 20 years in a closed environment, isolated from every person the crew had ever known, with no possibility of rescue, no possibility of turning back once a certain point is passed, no fresh food, no new faces, no seasons, no rain, no wind, no grass under their feet. 20 years in which the news from Earth, arriving at the speed of light, would grow progressively older by the time it arrived. In the final years of the journey, the crew would be receiving transmissions from Earth that were sent 4 years ago. They would watch elections whose outcomes had already been decided. They would learn of deaths and births that had already shaped the world they left behind. The psychological architecture required to sustain a human mind through this experience does not yet exist. Not because humans are fragile, though the body has its limits, but because no human being has ever been genuinely, completely, irreversibly cut off from their species for 2 decades. Even the most isolated expeditions in human history, Antarctic winter overcruise, submarine deployments, remote research stations, maintained some form of communication with the outside world. They knew that rescue was theoretically possible. They knew that voices on the other end of a radio transmission were hearing them in something close to real time. On an interstellar voyage, real-time communication ends the moment you leave the solar system. There is a word that appears repeatedly in serious discussions of interstellar human travel. The word is generation. Not in the biological sense, though biology is always nearby in these conversations, in the architectural sense. A generation ship is a vessel so large, so self-contained, so complete in its provision of everything human life requires, that the people who arrive at the destination are not the people who departed. They are the children, or the grandchildren or the great-grandchildren of the original crew. The voyage spans multiple human lifetimes. The ship is not a vehicle in the way a car or an airplane is a vehicle. It is a world. The concept has serious scientific and philosophical foundations. If we cannot accelerate a crewed spacecraft to speeds that make the journey survivable within a single lifetime, then the only alternative, short of technologies that do not yet exist, is to make the journey last multiple lifetimes. You build a closed ecological system capable of sustaining a population of several hundred to several thousand people indefinitely. You grow food, recycle water and air, manage reproduction, maintain technology, educate children, preserve knowledge, and sustain a social structure stable enough to prevent the kind of internal collapse that would doom the mission centuries before arrival. The engineering challenges are considerable but not obviously impossible. We already build systems capable of recycling air and water. We already understand closed-loop agriculture well enough to prototype it. We already know how to design radiation shielding for spacecraft, though at the scale of a generation ship the mass requirements become extraordinary. The International Space Station, which houses 6 people in conditions that require constant resupply from Earth, masses roughly 420,000 kilograms. A generation ship capable of housing a sustainable population for centuries would need to be orders of magnitude larger. But the engineering is almost the easy part. The harder question is sociological. What does it mean to be born on a ship? To grow up in an enclosed environment, knowing that the world your parents described, the blue planet with its wide skies and its oceans and its billions of strangers living their billions of separate lives, is receding behind you at a speed you can measure but never reverse. What does it mean to spend your entire life travelling toward a destination you will never reach? To know that your purpose, as defined by the civilization that built the vessel carrying you, is to produce children who will carry the mission forward, children who will in turn produce more children across centuries of travel through the dark. This is not a rhetorical question designed to make the concept seem dystopian. It is an honest inquiry into the social and psychological conditions that a generation ship would create, and serious researchers have taken it seriously. The concern is not that people born on such a ship would necessarily be unhappy. Happiness is remarkably adaptable. Humans have thrived in conditions that would seem, from the outside, almost unendurable. The concern is stability. Whether a society small enough to fit inside a spacecraft, isolated from the corrective pressures of the broader human world, cut off from new ideas, new cultures, new genetic diversity, would remain coherent across centuries. History offers limited guidance. Small isolated communities on Earth, island populations, remote valleys, strict religious enclaves, have sometimes maintained cultural continuity for centuries. They have also sometimes fragmented, radicalized, lost essential knowledge, or simply failed. On Earth, failure meant hardship. On a generation ship, a century from the nearest star in either direction, failure means extinction. The people who arrive at Alpha Centauri, if a generation ship ever makes the journey, will be as different from the people who departed as you are from your ancestors who lived 400 years ago. They will carry the mission in their culture, in their language, in their myths and rituals and inherited sense of purpose. But they will be, in every meaningful sense, a new people, born between stars, citizens of no world, arriving at a place no one who chose to make the journey ever lived to see. Let us step outside the ship for a moment, not metaphorically, literally. Let us think about what exists between here and Alpha Centauri, between the last familiar edges of our solar system and the first gravitational whisper of another star. Let us think about what interstellar space actually is, because most people, when they imagine the journey, imagine it as crossing a very large empty room, a vast but ultimately traversable void, dark and cold but fundamentally passive, something to be crossed rather than something to be survived. This picture is incomplete in ways that matter. Interstellar space is not empty. It is thin, extraordinarily thin by any measure derived from earthly experience, but it is not nothing. The interstellar medium, the name astronomers give to the material that fills the space between stars, consists of gas and dust distributed in quantities so low they would qualify as a near-perfect vacuum by laboratory standards. In the densest regions of the interstellar medium, there are roughly 1 million hydrogen atoms per cubic centimetre. This sounds like a lot until you consider that the air you are breathing right now contains approximately 27 million billion atoms per cubic centimetre. The interstellar medium is, by earthly standards, essentially nothing. But essentially nothing, encountered at 20% of the speed of light, becomes something else entirely. At that speed, each hydrogen atom the spacecraft encounters carries the kinetic energy of a high-velocity particle in a particle accelerator. The spacecraft is not drifting through a gentle fog. It is flying through a continuous, invisible storm of particle impacts, each one individually tiny, each one collectively part of a cumulative bombardment that, over 20 years of travel, could erode surfaces, damage electronics, and penetrate shielding in ways that engineers are only beginning to model with any precision. The dust is worse. Interstellar dust grains, typically between 1/100th and 1/10th of a millimetre in diameter, are sparse enough that a spacecraft travelling at low speeds would almost certainly never encounter one. At 20% of the speed of light, the probability calculation changes dramatically. A single dust grain struck at that velocity delivers energy comparable to a small explosive charge, not a nuclear explosion, but enough to punch through most materials we currently know how to build. A single impact of sufficient size could destroy a gram-scale probe entirely. A larger impact on a crewed vessel could breach a hull, disable a critical system, or worse. This is not speculation, it is physics. And it is one of the reasons that even the most optimistic breakthrough starshot scenarios involve sending not one spacecraft but hundreds or thousands of identical probes simultaneously, accepting that many will be lost to impacts or equipment failure and hoping that enough survive to return useful data. A kind of statistical exploration. Not a voyage but a volley. For a crewed ship, this approach is not available. You cannot send 1,000-generation ships and accept that most will be destroyed, which means that any serious crewed mission to Alpha Centauri must first solve the problem of shielding against the interstellar medium at high velocity. This requires materials that do not yet exist, in configurations that have not yet been designed, protecting systems that have not yet been built, across a journey for which we have no precedent whatsoever. The interstellar medium also carries magnetic fields, stretched thin across the void, remnants of stellar winds and ancient explosions. It carries cosmic rays, high-energy particles accelerated to near light speed by supernovae and other violent processes, streaming through space in all directions with enough energy to penetrate several meters of solid lead. The Earth's magnetic field and atmosphere protect us from most of these. A spacecraft in interstellar space has neither of these protections unless it generates its own, which requires mass, which requires energy, which requires fuel, which returns us always to the fundamental problem of how much a spacecraft can weigh, and how fast it can therefore go. Space, between the stars, is not an empty road. It is an environment, one that our biology did not evolve to inhabit, and that our technology has only barely begun to characterize. There is something else out there. something that most discussions of interstellar travel mention briefly, if at all, and then move past without lingering. Something that sits at the edge of the journey in a way that changes not just the physics, but the meaning of the entire undertaking. It is called the Oort cloud. You've probably heard the name. You may have a rough sense of what it is. A vast, distant reservoir of icy objects surrounding our solar system, the source of long-period comets that occasionally fall inward toward the Sun on journeys of thousands or millions of years. In the standard picture, the Oort cloud is a kind of remote storage, a frozen archive at the outer edge of the Sun's gravitational influence, interesting to astronomers but peripheral to everything else. What this picture underplays is the scale. The inner edge of the Oort cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, 150 million kilometers. The inner Oort cloud begins at 2,000 times that distance. Voyager 1, currently our most distant spacecraft, is just over 160 astronomical units from the Sun. It will not reach the inner edge of the Oort cloud for another 300 years. It will not exit the Oort cloud entirely for somewhere between 14,000 and 28,000 years. Read those numbers again slowly. Our most distant spacecraft, travelling at 61,000 kilometers per hour for nearly 50 years, has not yet reached the inner boundary of the cloud of objects that defines the outermost edge of our solar system. And crossing that cloud entirely will take tens of thousands of years. The outer edge of the Oort cloud extends to roughly 100,000 astronomical units from the Sun. This is almost exactly the halfway point to Alpha Centauri. The nearest star begins, in a very real sense, where our solar system ends, and our solar system ends much, much farther out than almost anyone intuitively grasps. When you imagine crossing the distance to Alpha Centauri, you probably imagined leaving Earth, passing through the familiar planets, crossing some notional boundary, and then entering interstellar space. The journey itself, the open water crossing between 2 stellar shores. What the Oort cloud reveals is that there is no clean boundary. There is no moment of departure where you leave the solar system behind and begin the interstellar voyage in earnest. Instead, there is a gradual, drawn-out leaving that takes longer than the entirety of recorded human civilization. The Sun's gravitational influence fades slowly across a vast volume of space filled with trillions of icy bodies, each one a relic of the solar system's formation, each one moving in orbits so large and so slow that they complete a single circuit only over millions of years. You're not crossing a room, you're crossing a continent, then an ocean, then another continent on the other side, and the ocean is wider than anything the word ocean is equipped to describe. The Oort cloud is the visual proof, the tangible structural evidence written in ice and gravity, that the distance to Alpha Centauri is not simply large. It is large in a way that resists every mental framework humans have developed for thinking about large things. It exceeds not just our experience but our intuition. It exceeds the metaphors we reach for to make it comprehensible. And when you finally clear it, when the last gravitational tendrils of our Sun release their grip and interstellar space opens genuinely ahead, Alpha Centauri is still more than 2 light-years away. You're halfway there. You've travelled farther than any human concept of far was designed to reach, and you are halfway there. The stars are not close to each other, not even the closest ones. The universe is not a neighbourhood. It is something older and larger and more indifferent than that word allows, and yet here we are, thinking about it, measuring it, planning, however tentatively, however audaciously to cross it. That impulse, the one that makes a species look at an impossible distance and begin calculating anyway, is worth sitting with for a moment before we go further. There is a star system at the end of this journey. that almost no one has described carefully enough. When people say Alpha Centauri, they usually mean a destination, a point on a map, a dot of light in the southern sky, the third brightest star visible from Earth, hanging just below the constellation Crux like a sentinel at the edge of the known. They say the name the way you say the name of a city you have never visited but always meant to, with a kind of comfortable familiarity that the actual place has never earned. Alpha Centauri is not a star. It is 3 stars. The first 2, Alpha Centauri A and Alpha Centauri B, form a binary pair. They orbit each other in an elliptical dance that takes roughly 80 years to complete one full cycle. At their closest approach, they are separated by a distance roughly equivalent to the distance between Saturn and our Sun. At their farthest, they drift apart to a separation closer to the distance between Pluto and our Sun. From Earth, they appear as a single point of light. Only a telescope resolves them into 2 distinct suns. Alpha Centauri A is slightly larger and brighter than our Sun, a G-type star burning with a warmth that planetary scientists find quietly encouraging. Alpha Centauri B is slightly smaller and cooler, a K-type star, orange-tinged and more sedate. Both are old stars by galactic standards, roughly 6.5 billion years old, nearly 2 billion years older than our own Sun. They have been burning steadily for longer than Earth has existed. Whatever conditions exist in that system have had enormous time to develop. The third member of the system is Proxima Centauri, the star Robert Innes found moving against the background in 1915. Proxima is a red dwarf, small, cool and faint, so faint that despite being the closest star to our Sun, it is completely invisible to the naked eye. It orbits the Alpha Centauri binary pair at an enormous distance, somewhere between 1/10 and 1/4 of a light year away, a gravitational association so loose that some astronomers have questioned whether Proxima is truly bound to the system or merely passing through on a timescale of millions of years. The current best evidence suggests it is gravitationally bound, but barely. A companion held by the lightest of celestial threads. Proxima Centauri is also, at 4.24 light-years, the closest of the 3 to Earth, and in 2016 something was found orbiting it that changed the texture of every conversation about Alpha Centauri that followed. A planet, Proxima Centauri b, a world with a mass at least 1.07 times that of Earth, orbiting in what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. The orbit takes just over 11 Earth days to complete. The planet is close, extremely close to its star by the standards of our solar system. But Proxima is so dim, so cool, that this close orbit places the planet within the range of temperatures that water requires to remain liquid, rather than frozen or vaporized. The discovery generated enormous excitement and, as good science always does, immediate and serious scrutiny. Because Proxima Centauri is not a quiet star. Red dwarfs, as a class, are prone to violent stellar flares, eruptions of radiation and energetic particles far more intense relative to the star's baseline output than anything our Sun produces. Proxima flares regularly and powerfully. In 2016, the same year its planet was confirmed, astronomers recorded a flare from Proxima that briefly made it 10 times brighter in ultraviolet wavelengths. A planet sitting as close as Proxima b, without a strong magnetic field or a thick protective atmosphere, would be bathed in radiation during these events at levels that would sterilize a surface and strip away an unprotected atmosphere over geological time. Whether Proxima b has a magnetic field is unknown. Whether it has a substantial atmosphere is unknown. Whether it is tidally locked, one face permanently turned toward its star in perpetual noon, while the other freezes in permanent midnight, is debated but considered likely given its orbital proximity. Whether liquid water exists on its surface depends on a chain of unknowns that current technology cannot resolve from a distance of 4.24 light-years. What is known is that it is there, a world, or something world-shaped, orbiting the nearest star, waiting with the patience of geology for someone to look more closely. The light you see when you look at Alpha Centauri tonight left that system 4.24 years ago. This is the kind of sentence that sounds simple and lands differently the longer you hold it. The photons currently entering your eye departed Alpha Centauri in the early months of a year that has already passed. They crossed the entirety of interstellar space, 4.2 light-years of vacuum and thin gas and ancient magnetic fields, and arrived here, at your eye, at this precise moment, having travelled their entire lives for the sole purpose, if purpose is a word we can use about light, of reaching you. What were you doing 4.24 years ago? Think about it honestly. Where were you living? What were you worried about? Who was in your life that isn't now or wasn't then that is now? The world was different in specific and personal ways. And while all of that was happening, while your life was arranging and rearranging itself in the ways lives do, this light was already on its way. Already crossing the void. Already committed to its arrival at a moment that, from the perspective of the photon, was always going to be now. This is what astronomers mean when they say that looking into space is looking into the past, not as a metaphor, as a literal description of what your eyes are doing every time you look at a star. The night sky is not a view of the universe as it is. It is a view of the universe as it was, at different moments in the past, layered into a single image that your brain assembles into something that feels like a present tense panorama. Alpha Centauri is showing you 4.24 years ago. The North Star, Polaris, is showing you approximately 430 years ago. The Andromeda Galaxy, visible to the naked eye as a faint smudge on a dark night, is showing you 2.5 million years ago. When you look at Andromeda, you're seeing light that left that galaxy before our species existed, before Homo sapiens had emerged, before the first stone tools of our genus had been struck. That galaxy's image, arriving at your eye tonight, has been travelling since a time when Earth was inhabited by creatures that were not yet us. The night sky is a museum. Every point of light is an exhibit from a different era, hung at a different depth, sending its message across a different span of time, and the deeper you look, the older the message. Now think about what this means for communication across interstellar distances. Not travel, just communication. A radio signal, which travels at the speed of light, takes 4.24 years to reach Alpha Centauri from Earth. If we transmitted a message today, the earliest anyone or anything at Alpha Centauri could receive it would be in 4.24 years. If they responded immediately, the earliest we could receive their reply would be 8.48 years from now. A conversation with our nearest neighbours, conducted at the speed of light, has a minimum round-trip delay of 8.5 years, not 8.5 seconds, not 8.5 minutes, 8.5 years. This is why the search for extraterrestrial intelligence, if it ever succeeds, will not resemble a conversation in any sense that the word currently implies. It will resemble finding a message in a bottle, reading it, writing a reply, throwing the bottle back into the ocean, and knowing that your grandchildren might be the ones who receive the answer, if an answer ever comes. The distance does not just make travel hard, it makes relationship hard. It makes contact, in any form resembling the contact between people who share a world, essentially impossible. We could know that someone was there. We could exchange information. The light you see when you look at Alpha Centauri tonight left that system 4.24 years ago. This is the kind of sentence that sounds simple and lands differently the longer you hold it. The photons currently entering your eye departed Alpha Centauri in the early months of a year that has already passed. They crossed the entirety of interstellar space, 4.2 light-years of vacuum and thin gas and ancient magnetic fields, and arrived here, at your eye, at this precise moment, having travelled their entire lives for the sole purpose, if purpose is a word we can use about light, of reaching you. What were you doing 4.24 years ago? Think about it honestly. Where were you living? What were you worried about? Who was in your life that isn't now or wasn't then that is now? The world was different in specific and personal ways. And while all of that was happening, while your life was arranging and rearranging itself in the ways lives do, this light was already on its way. Already crossing the void. Already committed to its arrival at a moment that, from the perspective of the photon, was always going to be now. This is what astronomers mean when they say that looking into space is looking into the past, not as a metaphor, as a literal description of what your eyes are doing every time you look at a star. The night sky is not a view of the universe as it is. It is a view of the universe as it was, at different moments in the past, layered into a single image that your brain assembles into something that feels like a present tense panorama. Alpha Centauri is showing you 4.24 years ago. The North Star, Polaris, is showing you approximately 430 years ago. The Andromeda Galaxy, visible to the naked eye as a faint smudge on a dark night, is showing you 2.5 million years ago. When you look at Andromeda, you're seeing light that left that galaxy before our species existed, before Homo sapiens had emerged, before the first stone tools of our genus had been struck. That galaxy's image, arriving at your eye tonight, has been travelling since a time when Earth was inhabited by creatures that were not yet us. The night sky is a museum. Every point of light is an exhibit from a different era, hung at a different depth, sending its message across a different span of time, and the deeper you look, the older the message. Now think about what this means for communication across interstellar distances. Not travel, just communication. A radio signal, which travels at the speed of light, takes 4.24 years to reach Alpha Centauri from Earth. If we transmitted a message today, the earliest anyone or anything at Alpha Centauri could receive it would be in 4.24 years. If they responded immediately, the earliest we could receive their reply would be 8.48 years from now. A conversation with our nearest neighbours, conducted at the speed of light, has a minimum round-trip delay of 8.5 years, not 8.5 seconds, not 8.5 minutes, 8.5 years. This is why the search for extraterrestrial intelligence, if it ever succeeds, will not resemble a conversation in any sense that the word currently implies. It will resemble finding a message in a bottle, reading it, writing a reply, throwing the bottle back into the ocean, and knowing that your grandchildren might be the ones who receive the answer, if an answer ever comes. The distance does not just make travel hard, it makes relationship hard. It makes contact, in any form resembling the contact between people who share a world, essentially impossible. We could know that someone was there. We could exchange information. We could learn about each other in the way you learn about a civilization from its literature, rather than from meeting its people. But the back and forth, the call and response, the living texture of actual communication, would be stretched across decades and replaced by something more like correspondence between strangers separated not by an ocean, but by time itself. And this too is part of what the distance to Alpha Centauri means. Not just the challenge of crossing it, the challenge of even reaching across it with a word. Let us talk about why we would go, not in the abstract language of exploration for its own sake, though that argument has genuine weight and deserves to be taken seriously. Not in the geopolitical language of national prestige or resource acquisition, though those forces have historically, driven more actual exploration than any purely scientific motivation, in the deeper language of what drives a species to look outward at all. There is another reason, one that operates on a longer timescale and speaks to something beyond individual psychology. It is called the long-term survival of the species. The Earth is not permanent. This is not pessimism. It is geology, astronomy, and thermodynamics speaking in unison. The Sun is a middle-aged star approximately 4.5 billion years into a lifespan of roughly 10 billion years. In approximately 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant, engulfing Mercury and Venus, and very possibly Earth. Long before that, in roughly 1 to 2 billion years, increasing solar luminosity will have raised Earth's surface temperatures enough to boil the oceans and end complex life as we know it. The planet has a timer. It is a long timer by any human measure, but it is a timer, and there are shorter-term risks. Asteroid impacts capable of causing mass extinction events occur on timescales of tens to hundreds of millions of years. Supervolcanic eruptions capable of altering the global climate occur more frequently. Pandemic diseases capable of threatening complex civilizations arise on timescales of centuries. The risks are real, distributed across different timescales, and none of them are zero. A species that exists on one planet is, in the language of systems engineering, a single point of failure. One sufficiently large asteroid, one sufficiently catastrophic eruption, one sufficiently virulent pathogen, and everything accumulated across the entire history of human consciousness is gone. Not diminished. Gone. Becoming a multi-planetary species is the most commonly cited solution to this problem. Mars is the obvious first step. It is close enough that travel times are measured in months rather than decades. It has resources that could potentially support a self-sustaining colony. It represents a second location for the human backup, a place where the knowledge and culture and biological diversity of our species could survive an extinction event on Earth. But Mars is in the same solar system, the same asteroid belt, the same sun. A rogue planet impacting the inner solar system, a gamma ray burst from a nearby stellar source, a supernova close enough to strip planetary atmospheres. These threats are not mitigated by having a colony on Mars. The solar system is one neighborhood. For genuine long-term resilience, for the kind of redundancy that actually protects against the full range of existential risks, a species needs to exist in multiple star systems. Alpha Centauri is the only realistic first candidate, not because it is hospitable, we do not know yet whether it is, but because it is closest. Because the investment in getting there, enormous as it is smaller than the investment required to reach any other star. Because if we ever develop the technology to send anything, probe or person, across interstellar distances, it will almost certainly be tested first on the shortest available route, and because Proxima Centauri b is there. Waiting. World-shaped and uncertain and close enough that the light from its star is already in your eye tonight if you know where to look. The distance to Alpha Centauri is not just a measurement, it is a threshold. On one side of it, everything humanity has ever done and been and built. On the other side, the first expansion beyond our solar cradle. The first time the word home would apply to more than one star system. The first time our species would stop being a local phenomenon and start being something that the universe, in whatever way the universe takes note of things, would need to account for differently. This is why the distance matters, not because it is large, but because crossing it would mean something. Something so large that we do not yet have adequate language for it. Something that would change not just where we are, but what we are. And it begins, as all things begin, with understanding exactly how far it is. With sitting with the number until it stops being a number and becomes a feeling. with letting the feeling settle into something that looks, from a certain angle, like resolve. There is a moment that comes in every long journey when the destination stops feeling like a goal and starts feeling like a question. Not a question about whether you will arrive, a deeper one, about what arriving would actually mean, about what you would find waiting on the other side of all that distance, and whether what you find would resemble what you imagined, and whether it matters if it does not. We have been building a picture of Alpha Centauri tonight from the outside, from here, from the only vantage point our species has ever occupied, and the picture is extraordinary in its detail for something so far away. 3 stars, an ancient binary pair older than our sun, burning steadily in their slow elliptical waltz. A red dwarf companion, faint and violent, held to the others by the most delicate of gravitational threads. A planet around that dwarf, world-shaped and silent, sitting in a zone where water does not automatically freeze or boil, waiting with the patience of rock for something to come close enough to see it properly. We know all of this from light, only from light, from the messages that travelled 4.24 years to reach instruments we built and pointed in the right direction at the right time, from the way a star's brightness dims when something crosses in front of it, from the tiny wobble a planet induces in its star as it orbits, a wobble so small it can only be measured by comparing the wavelength of starlight over months of careful observation. This is what human knowledge looks like at interstellar distances. Indirect, patient, built from the accumulation of signals so subtle that a century ago we lacked the instruments to detect them at all. What we know about Proxima Centauri b would fit in a short paragraph. Its minimum mass, its orbital period, its distance from its star, the fact that its star flares, the inference that it might be tidally locked. Everything else is extrapolation, careful reasoning from what we know about similar planets around similar stars in similar orbits, combined with the honest acknowledgement that we are reasoning from a sample of one inhabited world to conclusions about worlds we've never visited. We do not know if there is an atmosphere. We do not know if there is water. We do not know if the surface is bare rock or covered in something else entirely. We do not know if the flares from Proxima have stripped away whatever protection the planet once had, or whether some combination of magnetic field and atmospheric chemistry has preserved conditions that we would recognize as survivable. We don't know if anything is alive there, has ever been alive there, or ever will be. We know almost nothing, really, when you hold what we know against the full size of the question. And this is the thing about distance that is hardest to sit with. It is not only a barrier to travel, it is a barrier to knowledge. The universe keeps its secrets not through active concealment, but through simple geometry. Information travels at the speed of light. The further away something is, the older the information when it arrives, the harder to gather, the less complete. Alpha Centauri is close by cosmic standards. It is the nearest example of anything outside our own system. And even here, even at this minimal interstellar distance, the things we do not know vastly outnumber the things we do. What lies at the end of the journey is not a place we understand. It is a place we have sketched in broad strokes from very far away, using instruments of extraordinary precision pointed at a target of extraordinary faintness, and assembled into a picture that is probably right in its general outlines, and almost certainly wrong in ways we cannot yet identify. This is not a criticism of the science. The science is beautiful and careful, and represents the best that human ingenuity can currently achieve at this distance. It is simply an honest description of what knowing something across 4.24 light-years actually looks like. It looks like a sketch, a careful, evidence-based, scientifically rigorous sketch, but a sketch nonetheless. The journey would fill in the sketch, with detail, with colour, with the specific texture of a place that has been existing, in whatever state it exists in, for billions of years without anyone from Earth ever being close enough to see it clearly. And maybe that is enough reason, on its own, not survival, not science in the abstract, simply the desire to see the sketch finished, to know what is actually there, in the place that the light has been pointing toward all along. There is a quality that long distances share with long silences. They both ask something of you that shorter versions of the same thing do not. A short silence asks nothing. A long one begins to press. It asks whether you are comfortable with the absence of sound, with the space that opens when noise stops filling it, with what surfaces when there is nothing external to occupy attention. Most people, if they are honest, find long silences difficult, not because silence is harmful, because it is revealing. Long distances work the same way. The distance to Alpha Centauri is not simply a larger version of the distance from London to New York. It is a different kind of distance, not just in scale, but in what it does to the mind that tries to hold it. The distance from London to New York is inconvenient. It takes time. It requires a plane and a passport and the reorganization of a schedule. But it remains within the range of things the mind can hold without distortion. You can picture that ocean. You have some sense, experiential or inherited from images and stories, of what crossing it feels like. The distance to Alpha Centauri has no such grip on intuition. There is no inherited sense of it, no image in the cultural memory that captures it. Every attempt to make it feel real, every scale model, every metaphor, every comparison to the moon, or the distance to Mars, or the number of years Voyager would need, gets you closer but never quite there. The mind approaches it, and the mind slides away. Not because the mind is inadequate, though the mind was not built for distances like this. Because there is nothing in the accumulated experience of any human life that prepares the nervous system to feel 4 light years the way it feels a kilometre. And there is something worth noticing in that sliding. That particular quality of almost grasping and then losing the thread. It is not failure. It is information. It is the mind reporting accurately on the nature of the thing it is trying to hold. The fact that the distance resists being felt is the most honest signal we have of how genuinely large it is. If you could feel it completely, easily, without effort, it would mean you had replaced the real thing with something smaller that fit in its place. The discomfort of not quite being able to hold it is the distance itself pressing back. So perhaps the right response is not to try harder to make it fit, not to find one more metaphor or one more scale comparison that finally closes the gap between the number and the feeling. Perhaps the right response is to let it be as large as it is, to stop asking the mind to do something it was not made for, and instead simply rest in the presence of a fact that exceeds you. 4.2 light years, the fastest thing in the universe, travelling without pause, without rest, across a medium that is not empty, but that feels like nothing to anything that moves slowly through it. More than 4 years. Stars older than our own sun, burning in a slow binary orbit that has completed itself dozens of times since Earth first developed complex life. A small red dwarf holding a planet in its closest gravitational embrace, flaring and dimming, ancient and restless, lit by a fire that has been burning since before the first fish moved through the first ocean of our world. All of this is out there tonight, right now, as you lie wherever you are lying, as the room around you settles into whatever sounds a room makes when the night is quiet. The stars are where they have always been. Alpha Centauri is where it has always been. The light from it is crossing the void at the speed that light always crosses voids, arriving here in 4.24 years whether or not anyone is awake to receive it. The universe does not wait for us to be ready to look. It simply continues, at its own scale, in its own time, according to its own indifferent and beautiful rules. And we are here, small and curious and restless, at the bottom of a thin layer of gas on a rocky planet orbiting an ordinary star, looking up through that thin layer at a universe that extends in all directions further than the word further was ever designed to reach. And somehow, despite all of that, or perhaps because of it, the looking feels like enough. For tonight, it feels like enough. There is a word in Japanese that has no direct translation in English. The word is ma. It refers to the space between things, not empty space in the physical sense, not the void that physicists measure and cosmologists map, but the pause between notes in a piece of music, the gap between words in a conversation that carries as much meaning as the words themselves, the interval between one breath and the next in which something settles that cannot settle while breathing is happening. Ma is not nothing, it is the space in which things become themselves. Think about the distance to Alpha Centauri as Ma for a moment, not as an obstacle, not as a measurement, as a kind of interval. The space between one chapter of something and the next, between what our species has been, for all of its history on this planet, and what it might become if it ever crosses that distance, between the version of humanity that has only ever known one solar system and the version that would know two. That interval is 4.24 light-years wide. It is filled with thin gas and ancient magnetic fields, and the occasional dust grain moving slowly through the dark. It is crossed by light and by radio signals, and by the occasional high-energy particle accelerated to near light speed by the violence of distant stellar deaths. Nothing with mass and intention has ever moved through it from our side. Nothing has looked back at our sun from the middle of it and seen both stars simultaneously, our own and Alpha Centauri's, hanging in the same sky for the first time. The interval is uncrossed. And there is something in that fact, something that might be loss or might be anticipation, depending on the angle from which you approach it, that deserves a moment of quiet attention before we continue. Everything our species has ever done has happened on one side of that interval. Every war and every peace treaty, every discovery and every forgetting, every child born and every elder buried, every song written, and every language that fell silent before anyone thought to record it. Every act of cruelty that history has preserved, and every act of kindness that history forgot immediately. The entirety of human experience, the full accumulation of what it has meant to be this particular kind of creature on this particular kind of world, fits on one side of a gap 4.24 light-years wide, and on the other side 3 stars older than our own, turning slowly in the dark, and maybe, a rocky world with a thin atmosphere and a surface that has never been touched by anything that wondered about it. The ma between these two things is not empty. It is full of the weight of what crossing it would mean. Not the crossing itself, not the engineering or the physics or the decades of travel, but the meaning of it. The irreversible change in what we are as a species the moment any part of us exists on both sides of that interval simultaneously. There are crossings in history that change the nature of the thing that crossed, not just its location but its character. When the first humans moved out of Africa, they did not simply relocate. They became something slightly different in the moving. The crossing shaped them. The new environments they entered selected for new traits, demanded new knowledge, created new stories and new ways of organizing the world. The crossing was not just transit. It was transformation. The crossing of 4.24 light-years would be the largest version of this that our species has ever attempted. And the transformation on the other side, whatever it looked like, would be proportional to the distance. You do not cross the gulf between stars and come out the same kind of thing that went in. What comes out would still be human. It would carry human language and human memory, and the human sense of what matters and what doesn't. but it would be human in a way that has been changed by the crossing, by the years of silence, by the shrinking of the sun to a star, by the growing of another star until it filled a sky that no human eye had ever seen before. It would be the next sentence in something that began a very long time ago, in a body of water on a planet that, from Alpha Centauri, is invisible. The night is quieter now, not literally perhaps. The sounds around you are whatever they have always been. The hum of something electronic, the distant movement of air, the settling of walls as temperature shifts by fractions of a degree. Whatever sounds a sleeping world makes when most of it has gone still. But something in the quality of thinking changes over the course of a long night. The edges soften, the precision that felt necessary at the beginning, the need to get the numbers exactly right, to follow the logic all the way to its conclusion, to hold every implication clearly and not let any of it slide, that precision relaxes. Not because the numbers stop being true, they remain exactly what they were. 4.24 light years, 73,000 years for Voyager, 20 years at 20% of the speed of light, 8.5 years for a round-trip exchange of signals with our nearest neighbour. The numbers are still there. They just feel different now, less like walls and more like furniture, part of the room rather than the whole of it. This is what long thinking does. It does not resolve the difficulty. The distance to Alpha Centauri is just as large at this point in the night as it was at the beginning. The engineering challenges have not simplified. The biological obstacles have not dissolved. The philosophical weight of what it would mean to cross that distance has not become lighter. Nothing has been solved. And yet something has shifted, in the quiet way that things shift when you have been with a thought long enough for it to stop being unfamiliar. There is a particular kind of peace that comes not from understanding something completely, but from becoming comfortable with the shape of what you do not understand. From learning where the edges of a thing are, even if what lies beyond those edges remains unclear. We have spent tonight walking the perimeter of something very large. We have measured it from different angles, stood at different points along its edge, and looked outward and inward, tried different scales and different metaphors and different ways of approaching the central fact. The central fact remains 4.2 light years, the terrifying distance to Alpha Centauri. Terrifying is the right word. Not because the distance threatens us. It does not. It simply sits there, between us and the nearest other star, doing nothing, requiring nothing of us. The terror is quieter than that. It is the terror of scale, of being a particular size in a universe that is indifferent to your size, of discovering that the nearest example of the thing most fundamental to your existence, a star, a sun, a source of light and heat, and the energy that drives every living process, is separated from our own by a distance that makes our fastest machines seem like toys, and our longest lives seem like moments. But terror, held long enough, changes. It does not become comfortable exactly. It does not stop being what it is, but it becomes familiar, and familiar things, even large and difficult ones, can be lived with, can be thought about without the thought itself feeling like a threat, can be incorporated into the background of a life in a way that adds depth rather than weight. The distance to Alpha Centauri is part of the background of every human life, whether or not any given person has ever thought about it. It is there every night. The light from that system arriving here continuously, crossing the void that separates us, entering eyes that are mostly pointed elsewhere, mostly concerned with closer things, the ceiling above, the room around, the thoughts that accumulate between waking and sleeping. But sometimes, on the right kind of night, a person looks up at that point of light in the southern sky and holds still for a moment and lets the distance be as large as it is. And in that moment, something ancient and quiet and very much alive in the human animal recognizes that it is looking at something it cannot reach, and wants to anyway, and finds in that wanting not despair, but a kind of orientation, a sense of direction that doesn't require a destination to be reachable to be real. The distance remains, the wanting remains, and that for tonight is enough to rest in. There is a question that serious people have asked seriously, and that deserves a serious answer before this night is over. Not whether we can go, we have spent enough time with that. The answer is not yet, and possibly not for a very long time, and possibly with technologies we cannot currently imagine, and possibly not within any time scale that anyone alive tonight will witness firsthand. That much is clear. The question is different. It is this: does it matter that we want to? Because wanting by itself does not cross distances. Desire does not produce propulsion. The history of human longing is full of things that were wanted intensely and never achieved. Species go extinct wanting to survive. Civilizations collapse wanting to continue. Individual lives end wanting more time. The universe is not moved by wanting. It does not rearrange itself to accommodate the preferences of creatures who happen to have developed the cognitive capacity to know what they want and to feel the ache of not having it. So does the wanting matter? There is one answer that comes from history, and it is genuinely complicated. Every significant expansion of human presence and knowledge in the last 5 centuries has been preceded by a period of wanting that preceded the capability to act on that wanting. The people who first imagined circumnavigating the globe did so long before the ships existed to attempt it. The people who first conceived of human flight did so in eras when the engineering was not merely incomplete, but in some cases not yet conceivable. The people who first dreamed of leaving Earth's atmosphere and touching another world did so when the concept of a rocket powerful enough to escape gravity was still largely theoretical. In each case, the wanting came first. The capability followed, shaped by the wanting, driven by it, funded by the cultural and economic energy that accumulated around it. This is not a law, it is a pattern. And patterns have exceptions. Some things have been wanted for a very long time and have not arrived. The gap between wanting and being able is not always closed. History is also full of dreams that outlasted every civilization that dreamed them, that dissolved into other preoccupations or were abandoned when the difficulty became clear. That seemed achievable from one century and impossible from the next. The honest position is that we do not know which of these Alpha Centauri will turn out to be. We do not know whether the wanting that currently exists, distributed across millions of people who find this distance compelling, who work in the fields of physics and engineering and astronomy and astrobiology, who watch the night sky and feel the pull of that particular point of light, will accumulate into capability within any time frame we can identify. What we do know is that the wanting is real, that it exists, that it is not trivial or irrational or based on a misunderstanding of the difficulty. The people who want to reach Alpha Centauri know exactly how far it is. Many of them have spent their careers working on the specific problems that the distance creates. They are not naive about the obstacles. They want to go anyway. And that wanting, whatever its ultimate fate, is one of the most interesting things about the species that produced it. A creature small enough to hold in one hand, living on a planet that is itself invisible from the destination it is dreaming about, wanting to cross a distance that its fastest machines cannot cover in 100,000 years. It is not rational in any narrow sense of the word. It is something older than rationality, something that was already present in whatever ancestor first looked at the far side of a valley and began walking toward it without knowing what was there. Let us talk about time one more time before we let it go. not the time the journey takes. We have measured that from several directions, and the measurements have not become more comfortable with repetition. 73,000 years for Voyager, 20 years at 20% of the speed of light for a gram-scale chip riding a laser beam, centuries for a generation ship. These numbers are what they are, a different kind of time, the time we're already in, right now, tonight, as you lie in whatever position has become comfortable over the last few hours. Light is arriving at Earth from Alpha Centauri that left that system 4.24 years ago. And light is leaving Earth tonight, in all directions, carrying with it the electromagnetic signature of everything we are broadcasting. Television signals, radio transmissions, radar pulses, the incidental radiation of a technological civilization conducting its business without much thought for where the signals go after they leave the atmosphere. This outgoing light, this accidental message we have been sending into the universe since the middle of the last century, is currently spreading outward in a sphere that grows larger by 1 light year per year. The oldest of our deliberate and accidental transmissions have now travelled roughly 80 light years from Earth. They have passed more than a dozen star systems. They are currently washing over stars whose names most people have never heard, carrying fragments of everything we have been for the last 8 decades. Alpha Centauri received our first radio transmissions roughly 75 years after they were sent. Right now, an observer at Alpha Centauri with a sufficiently sensitive antenna could, in principle, be detecting signals from Earth that originated in the middle of the 20th century. Not clear signals, not an intelligible broadcast. The signals have weakened enormously over that distance, spreading across an ever larger sphere, diluting to levels that would require instruments of extraordinary sensitivity to detect even in principle. But the signals are there, mathematically, physically, actually there. We have already reached Alpha Centauri in this sense. The lightest, most attenuated, most accidental version of ourselves has already made the crossing, already arrived, already passed through whatever is there, and continued onward into the deeper dark beyond. This is not nothing. It is not the same as a probe with cameras and sensors, not the same as a human being standing on a surface and looking up at an unfamiliar sky. But it is a kind of presence, an electromagnetic shadow of our civilization, ghostly and unintentional, already distributed across the nearest stellar neighbourhood. If there is anything in the Alpha Centauri system capable of detecting and interpreting electromagnetic signals, and the likelihood of this is unknown in either direction, it has already had 4 decades to wander about us, to detect the pattern, to notice that the signals are structured in ways that suggest origin in a specific location, to point something back at that location and wait. Any reply sent at the speed of light would take 4.24 years to arrive here. We do not know when or whether anything was sent. We do not know what form it would take. We are not currently operating any receiver specifically calibrated to detect a response from that direction. The conversation, if it is happening at all, is happening on a timescale that does not fit inside a human life. It began before any person currently alive was born. Any response, if one ever comes, may arrive after most people reading this have died. The universe operates on schedules that do not consult us, and yet these signals travel, and yet the distance is being crossed, even if only by light, even if only by accident, even if no one on the other end is listening or ever has been. The universe does not require witnesses to be real. The crossing happens whether we are aware of it or not, whether we are watching or not, whether we survive long enough to know what the crossing finds. The stars are still there. This seems like an obvious thing to say, but it is worth saying slowly at this point in the night, when the thinking has been long, and the distance has been measured from many angles and the mind has travelled further than the body will ever go. The stars are still there, Alpha Centauri is still where it has been for the entirety of human history. Its light is still, arriving at the rate it has always arrived, crossing 4.24 light-years of interstellar space at 300,000 kilometers per second, entering the atmosphere above you, scattering slightly in the molecules of air, reaching the surface of the Earth, passing through windows and walls and eyelids, existing whether seen or not. The universe is not waiting for us to look at it before it continues being what it is. There is something in this that functions like comfort, if you let it. Not the false comfort of things being simpler than they are. The distance is not small, the challenges are not trivial, the gap between where we are and where we would need to be to meaningfully engage with that distance is enormous by any honest accounting. None of this has changed in the course of this night. None of it will change because we've thought about it carefully. The comfort is of a different kind. The kind that comes from knowing that what you're looking at is real. That it has been there for longer than any question you could ask about it. That it will be there after every question has been asked and answered and replaced by new questions that previous answers made possible. The distance to Alpha Centauri is not a problem waiting to be solved before it becomes permanent. It is already permanent. It is already real. It is already, in the most literal sense, the actual situation our species finds itself in, whether we think about it or not. And knowing the actual situation, even when the actual situation is difficult, is better than not knowing it. This is one of the few things that seems to remain true regardless of context. That accurate perception, even of uncomfortable things, provides a kind of ground to stand on, that comfortable illusions cannot. You can navigate from where you actually are. You cannot navigate from where you wish you were. So we have spent this night with where we actually are. We are on a planet orbiting an ordinary star in an unremarkable corner of a mid-sized galaxy. Our nearest stellar neighbour is 4.24 light-years away. Our fastest spacecraft would take 73,000 years to reach it. Our most ambitious current proposals might reduce that to 20 years, for an unmanned probe the size of a postage stamp. A proposal that requires technology we do not yet have, and funding we have not yet committed. The physical environment between here and there is actively hostile to everything we know how to build. The biological requirements of surviving the journey in a human body are largely unsolved. The psychological demands of the crossing are genuinely unprecedented, and we are the species that knows all of this and continues to find the distance compelling rather than simply discouraging. That is also part of where we actually are. The distance is terrifying, and we are the kind of creature that looks at terrifying distances and feels something that is not quite fear and not quite hope, but something that sits between them, something that has no clean name, something that makes us point instruments at the sky and measure the wobble of distant stars and calculate the odds and argue about propulsion systems and write equations on whiteboards in the middle of the night. Whatever that something is, it is as real as the distance itself. Maybe more durable. Let the numbers go for a little while. They have done their work. The distances have been measured and remeasured and held at different scales and compared to familiar things, and found to exceed all of them. The physics has been laid out as honestly as it can be. The biology has been acknowledged. The philosophy has been sitting quietly in the background, patient as a star, waiting to be noticed. Let all of that settle now. Let it find its place in whatever order the mind arranges things when it stops actively sorting them. There is a quality to late-night thinking that daytime thinking does not quite achieve. Not because the thinking is more accurate, it often isn't, but because something in the quality of attention changes when the world has gone quiet around you. The urgency lifts. The sense that you need to arrive somewhere before the time runs out, that the thinking needs to conclude, that understanding needs to be packaged into something transferable before the moment passes, that lifts, and what remains is something simpler and in its own way more honest, just the presence of a mind in the presence of a fact. No agenda beyond the presence itself. You're lying somewhere on the surface of a planet. The planet is rotating. The rotation is carrying you slowly beneath a sky full of stars, most of them so distant that the light arriving from them left before humans existed, before mammals existed, before complex life had colonized the land. The sky is an archive of distances so vast that the ones we have been discussing tonight, 4 light years, 400 light years, 4 million light years, are merely the nearest shelves of a library that extends to the edge of what the universe has had time to become since the beginning. And among all of those lights, one particular grouping, barely visible without a telescope from the northern hemisphere, easily visible from the south, sits at a distance that is, by the standards of the library around it, almost laughably close. Almost nothing, practically next door. 4 light years, 200,000, in a universe 13 billion light years across in every direction. And from here, from the perspective of a species that has not yet worked out how to send its machines there in less than geological time, that almost nothing, that practically next door is the most terrifying distance in the world. Not because it is insurmountable, we do not know that, not because it represents the limit of the possible. Physics has not drawn that line here, but because it is the first step, the threshold between one kind of existence and another, the place where the map of human presence ends and something unmapped begins. And the first step is always the one that requires the most from you, not physically, psychologically. The acknowledgement that the journey is real, that the destination exists, that the distance between them is the distance between who you have been and who you might become. Every journey begins before the first step. It begins in the mind that decides the destination is real enough to walk toward, that the ground between here and there, however difficult, is ground and not simply absence, that the gap between what is and what might be is not a wall but a road. The road to Alpha Centauri is 4.24 light-years long. It has not been walked yet. That is the most honest thing that can be said about it, and the most open. The room is very quiet now. Whatever sounds existed at the beginning of the night have settled into a background so familiar it no longer registers as sound at all. The body has made its accommodations with the position it has been in. The breathing has found its own rhythm without anyone asking it to. The thinking that was sharp and sequential a few hours ago has become something softer, less directed, moving through the images and numbers and ideas of the night the way water moves through a landscape it has crossed before, finding the low paths without effort, pooling briefly in certain places and moving on. This is the right state in which to say the last things, not because the last things are less important, but because they belong to a different register than the first ones. The first things required attention. The last things require something closer to receptiveness. The willingness to let something arrive rather than going out to meet it. Here is what arrives. The universe is very old and very large and almost entirely indifferent to the existence of any particular arrangement of matter within it. This is not a new thought. It is perhaps the oldest thought that scientific inquiry has produced, the slow accumulation of evidence over centuries that the cosmos was not made for us, does not notice us, and will continue long after we're gone without registering our absence. The stars burned for billions of years before our sun formed. They will burn for billions of years after our sun exhausts itself. Whatever happens on the small rocky planet orbiting the ordinary star in the quiet arm of the ordinary galaxy is, from the perspective of cosmic scales, a local phenomenon of no particular duration. This thought, held carelessly, becomes bleak. It becomes the kind of emptiness that certain temperaments find in large spaces, the vertigo of scale, the sense that nothing matters because everything is tiny. But held carefully for long enough, in the right kind of quiet, it becomes something else. If the universe is indifferent, then every instance of caring is remarkable. Every mind that has looked at the sky and found it beautiful has done something the universe did not require and did not ask for. Every scientist who has spent years measuring the wobble of a distant star to determine whether a planet might orbit it has devoted a human life to a question that the universe posed by accident and cannot itself answer. Every person who has lain awake at night and felt the pull of a light source 4.24 light-years away has participated in something that has no cosmic sanction and no cosmic audience and matters anyway, in the way that things matter when the only court they appear before is the consciousness of the creature attending to them. Alpha Centauri does not know we are looking. Proxima Centauri b does not know it is being dreamed about. The interstellar medium between here and there does not know it is being measured, mapped, considered as an obstacle, incorporated into calculations made by beings who have existed for a fraction of a % of the time it has been drifting. Only we know. Only we find it remarkable. Only we feel the combination of smallness and curiosity and longing that this distance produces in the particular kind of animal that produces it. And that particular combination, smallness and curiosity and longing in the presence of something vast, is the most human thing there is. More human than language, more human than tools, more human, possibly, than any other single characteristic this species can point to. We are the creatures who look at the distance and feel it, who measure it and are not satisfied, who imagine crossing it and find the imagining insufficient and want the crossing itself. The distance to Alpha Centauri is 4.24 light-years. We are still here. We have not stopped looking. Before you sleep, one last thing. Look up if you can, not at the ceiling, through it, past it, into the dark beyond the atmosphere that has been holding you in its thin, warm embrace for every moment of your life without asking for acknowledgement or gratitude, past the satellites tracing their silent arcs above the clouds, past the moon, wherever it is in its cycle tonight, its face lit or darkened or somewhere between, past the planets, those wandering lights that the ancients tracked with such careful attention because they moved when the other stars did not, past all of it, through all of it, to the stars themselves. They are all still there, and somewhere in the southern sky, or below your horizon, if the geometry of tonight does not favour it, there is a point of light that has been part of this story longer than any of the words used to tell it, a point of light that was burning before Earth existed. That will be burning in some form, long after every city built by every civilization our species produces has returned to the dust that made it. A point of light that is not one star but three, holding each other in gravitational patterns too slow for any human lifetime to witness in full, 4.2 light-years away. The terrifying distance. We have spent tonight with it. We have measured it and scaled it and tried to feel it and partially succeeded and partially failed in the way that honest attempts at impossible things always do. We have followed the physics as far as the physics goes and then stood at the edge and looked at what the physics cannot yet reach. We've thought about the machines and the people and the time and the longing and the meaning and the quiet fact of a universe that continues regardless. If something shifted tonight, even slightly, in how you hold that distance, then the night has done what it was meant to do, not to make the distance smaller. It is what it is, but to make your understanding of it a little more accurate, a little more honest, a little more comfortable with the size of things as they actually are, rather than the size of things as we might prefer them to be. The universe is not cruel in its scale. It is simply scaled to its own purposes, which are not our purposes, and which we are only beginning, with instruments we built yesterday in cosmic time, to measure and describe and partially understand. And we are here, still looking, still finding the looking worthwhile. If this journey through the dark has been something you want to carry forward, carry it. Share it with someone who might find it useful. Leave a comment about where you are in the world tonight, what time it is there, what the sky looks like if you can see it. These things matter in the small and real way that small and real things matter, which is more than the universe requires of them and exactly as much as they deserve. Subscribe if you want more nights like this one. There are more distances to sit with, more facts that are large and difficult and worth the time, more points of light that have been waiting patiently, for longer than the questions we bring to them, for someone to look carefully and ask what they are. Sleep well. The stars will still be there when you wake.